Okay, so the homework. You had this graph. And if you read carefully, you saw that it was a rate of change graph. So on the x-axis here was months, and on the y-axis would be giving you the number of insects per month. So right here, say this point right here, at 0.4 months, there's a point on the graph right there. And so what does that point represent about this situation? What does that point represent about the situation? Andre? Yeah, 0.4. Yeah, so at 0.4 months, you said the rate of change is 30 insects per month. So what's happening to the population right here? What's happening to the population, just generally? Increasing or decreasing? Increasing, right? Increasing. So rate of change graph. Because the rate of change is positive, the population of insects is increasing. Now the rate is going down, but it's a positive rate, so the number of insects is going up this whole time, right? It's going up this whole time. So the most number of insects that you have in the first month is when? At the end of the month. This is increasing population the whole time. Increasing population the whole time. Okay, sounds like most of you got that. Good, okay, and so then I said, show a constant rate at these different, at 25, at 45, and 60. Do any of those relate to estimating the rate of change for the real rate? The one in the middle would be like a kind of somewhat of an estimation. This first one's way too low. The rate's always greater than that. 60 is too high. The rate's always less than that. So maybe this one in the middle would be a good rate for that. And then if we did it for if I continued doing it for 0.2 month increments, I might get something like this, just as estimates of the real rate, but trying to reproduce that real rate as constant rates, right? Trying to reproduce the real rate function, changing rate, as in constant rates. We could come up with something like this. Okay, so for those of you who did not have me for Calc 1, you may be seeing something like this. You say, oh, this is really just rectangles, right? And we're going to calculate areas of those rectangles. Okay? But what does a population of insects have to do with area? It doesn't, right? It's population, it's number of insects. It's number of insects. So we don't want to think about it this way. Right now, anyway. Okay? We want to think about this in terms of rate of change and accumulation of number of insects, not areas of rectangles. So when we think about we're going to think about it this way, that those black steps are not creating rectangles, but they're trying to reproduce the actual rate function with constant rates. That's the way we want to think about it. We're trying to reproduce, we're making a new function that's trying to be like the blue rate function, but using constant rates. So that would have nothing to do with rectangles, right? That would have nothing to do with rectangles. Okay? We'll get to rectangles later, but that's when we're talking about geometry, more geometry, and not rate of change and accumulation. Okay, and so then for this, so if I have my first rate here is 45, so M1, 45, M2, I don't know, 42, M3, 22, M4 is 16, and M5, 24. Now, you may have chosen different constant rates, but and you also may have chosen different interval width. I didn't tell you the interval width, okay? So I just went with the lead from the question before that talked about for the first 0.2 months, and I just went with 0.2 month intervals, but you could have done 0.4 month intervals or 0.1 or something like that. If you do 0.2, you're going to get numbers similar to this or maybe a little different. And so then how do we get the total insect population at 1 month? So at 0, population is 105. So before we accumulate any insects according to this rate, we have that 105, right? And then we're going to accumulate here by according to these constant rates. And so actually this is an approximation, right? So I should say it's approximately 105 plus. And how do we get the total change in the quantity? Total change in the quantity at a constant rate is what? Just generally. M times change in x. M dx, right? dy is m dx. That's our bedrock for constant rate of change. So we're going to do m times change in x plus m times change in x. 2. Plus all the way to 25 times the change in x. And anybody remember about what that turns out to be? 135-ish, and everyone will have a slightly different answer. 35, and that's insects. Okay, so we can get this approximation by using constant rates that are trying to be like the real rate function. Because constant rate of change gives us this real easy math, right? M times the change in x. We can get a change in the amount. Okay, so notice that when we're doing this, we're always adding what? We're always adding some m times dx, right? So we can show that symbolically. Instead of writing that over and over again, we can show that symbolically with this symbol, right? Which means sum. I'm summing up a bunch of, and they're all the same, right? I'm summing up a bunch of things that are all the same. They're all like this: m dx, m dx, m dx. It's just the only thing that's different is my m, so I can say m sub I, and I goes from, I starts at 1 and goes to 5. So this is what this notation means. It means sum up a bunch of things that all look alike. The thing that's different about each one is just the value of m. So we're going to get a different value of m each time we add the next one on. So this is called our summation notation. So that's capital Greek sigma means sum. And so this is an alternate way. Instead of, especially when you have maybe 20 or 50 or 100 of these, it's going to be a lot easier to write just that one statement than to try to write out all 50 or all 100 of the individual terms that you're adding together, okay? So this is not meant to be scary. It's meant to be concise and save us writing, right? So you just got to know what it means. Summing up things that all look like this, and then the first one is going to have M1, the second one's going to have M2, M3, M4, M5, etc. Does that make sense? Okay. So then rather than look at, sometimes it's convenient, rather than to kind of be eyeballing from the graph and trying to place this constant rate just in the right place, we can do something more systematic and something that might be a little quicker, and that is just to, instead of using an eyeballed rate, we use the rate, say, the actual rate at the left side of every interval. So we look at every interval from 0 to 0.2, and we say, what's the rate at the left side of that first interval? What is the rate? Should make it bigger. What is the rate at the left side of that first interval? 30. So let's just say, even though it's a low estimate, we'll just make the constant rate 30 for that whole interval. And the same thing for this. So what is the constant rate at the left side of this second interval? I'm sorry, what is the actual rate at the left side? About what? 57, 58, up here at that point. Okay, so then we'll say for that second interval, the constant rate will be the same as the actual rate at the start of the interval, the left side. What about the third interval? What's the actual rate? About 30? Fourth interval? 13, 14, yeah, 14, maybe 14 or 15. And then the last interval at the left side? $18 or $19. Okay, so this is an alternate way to do it. Rather than a little more systematic and just mechanical, rather than trying to estimate an eyeball by your eye. And this is also a lot more convenient when you have lots and lots of intervals, right? Instead of you have to do each one, you don't want to do each one by hand. You just want to say, okay, we're just going to use the actual rate at the start of the interval, the left side of the interval, to be the constant rate for that whole interval. Okay, so this is called using a left side approach. So the left side approach and notice that it's not because these are like flags flying left, because they're actually like flags flying right. Okay, so what does left side approach mean? It means we're using the rate at the start or the left side of the interval to be our constant rate for the whole interval. So it's a left side approach to creating the pretend rate function. Okay, you could also use a right side approach. You'd pick off the actual rates on the right side of the interval, and then that would be the constant rate for each interval, would be the rate at the right side interval. You can use midpoint, right? What's the rate at the midpoint of each interval? Make that be the constant rate for the whole interval, okay? Left side is maybe most common and most convenient because it's the starting value. Okay, so going back to the flag lowering. So let's take a look at the flag lowering example using this left side approach to build these build a pretend rate function. Okay, so here's that rate function, and we want to think about functions as emerging as that variable x increases. What was our variable x in this case? Remember? So we can refresh here. X was time in seconds since the flag, I'll just do seconds here. Seconds. That was the time in seconds since the flag was at the top of the pole. Okay, and so when you see a curve or a function, you want to think of it this way. Think about it as x is varying, right? X starts at 0 and varies, and then that function emerges as each individual point is plotted, right? So we're plotting an infinite number of points as x increases. Okay, so we could do, if we did a left side approach with delta x of 0.3, it would look like this. And so now I'm showing the pretend rate function emerging. Can you see the actual one still? Barely? Okay, so how does this, with 0.3, delta x of 0.3, how does this do at recreating the original true rate function? How does it do? Is it a good reproduction of it, or not so great? Oh, so you're saying that the error will, if you take a long period of time, the error will kind of cancel out, low and high error. That's true. Yeah, that's a good point. But I'm just kind of looking at the graph, comparing the graph of the original function to the graph of the step function or our constant rate function. And so in general, how is the constant rate function doing? Not great. You see, a lot of it is the negative 0.75, which we know that's a lot of it. But you know, if I turn it off, if I turn off the, would you be able to, from that, would you be able to sketch what our rate function was if you had that? Sketch the original rate function. You wouldn't be able to, right? So what we want to do is we want to get a better pretend rate function. We want to get still based on constant rates, but that does a better job reproducing the actual rate function. How do we do that? All of you know, right? So by choosing a smaller interval, so here is 0.17 interval instead of 0.3. Here's 0.17. Okay. So better, still not great. So here's them both plotted at the same time. So it's better, but how can we do even better? Yeah, so the smaller your interval is, the more your constant rates, the better your constant rates will do at reproducing the original true rate graph or curve. So here's 0.03. So I showed you, I start with 0.3. Here's 0.03. So every 0.3. Now we really see it taking shape, right? So now we can really see that that original function. If I don't show it now, but you can still kind of see what it is now, right? But still, this is all made up of constant rates, such that we could get the little change in height for each one, add them all up, and get a total change in height. But what, you know, better results would require a lot more work, right? So if you want something better, you got to work harder for it. That'd be a lot of work. We don't want to do that by hand, right? Because that's something like 50 or 40 or 50 intervals, and so that would take a lot of work by hand. Okay, so, and then how could we? So now we're getting really close here, and so how do we think about reproducing the exact rate function, but still with constant rates, so that we could sum up the changes and get the total change? So we think about just super small intervals. So now that is still, I'm still showing you a sequence or a series of constant rates. But you see how it's mimicking that original rate function like almost perfectly, right? So I'll show them both. That's both. That's just the pretend rate function. Okay, so let's review where we've been so far. Oh, that's for my kids. All right, let's see here. Back to, so let's review. We're on this journey of making sense of this equation that represents the fundamental theorem of calculus, and we talked about, and so what is it for? It's for calculating an amount or amounts of change. That's what we did, right? So we've done that with the flag example. We're calculating the change in height of the flag, and you guys did it for homework. Change in number of bacteria or a total number of bacteria. What was it bacteria? Insects. Okay, insects. All right, so our principle one was constant rate of change. And we said, what does 60 miles per hour mean? So, what does 60 miles, anybody remember? What does 60 miles per hour mean? What that means, so for every hour that you go, your distance changes 60 miles. For any change in time, you go 60 miles. Right. So it's a lot more than just how far you go in an hour, right? That tells you how far you go in any change of time, right? How far do you go in any change of time? How far do you go? So what would it be? right? So it tells you that for any change in time dx, your change in distance is 60 times that change in time. So it tells us a lot more than just you go 60 miles in an hour. It tells you how far you go in any amount of time. But you just multiply by 60, right? Take any change in time, multiply by 60, you get the change in distance. So this is our very important principle of dy equals mdx. Okay, and then principle 2, we said lots of things in the real world don't change at a constant rate. Realistic rates are usually changing rates, and so we looked at the flag lowering. It doesn't come down steady when someone's pulling hand over hand like this, right? There's a pause, and it's kind of slows down to 0 in between each hand change, right? So the principle 3 then would be creating a pretend rate function. So we don't have a constant rate of change, but we want to use that easy mathematics of constant rate of change in order to talk about finding a total change when the rate is changing. So what? We want to mimic the rate function with constant rates so we can apply principle 1. And we're going to add up the changes to estimate the total amount of change. This was your homework, right? That's what I went over just a second ago. And we said that that's the total change is the sum of many m delta x. So we're talking about dx, so I'll do dx. Okay, m dx. This is principle 3. Principle 4 is we want to get a better result. Principle 4, how do we get a better result? Because this is just an estimation, right? We've mimicked the function with these constant rates on intervals, but that's not the real original rate function, right? That's not the original rate function. So how can we do better than a pretend rate function? Make smaller intervals, right? So that's principle 4, make more smaller intervals. Okay, a better pretend rate function means a better estimate of your total amount. A better pretend rate function results in a better estimate of your total amount because your rate function is doing a better job of mimicking the real rate function. Better ingredients, better pizza. Papa John's. Right? So better pretend rate function, better estimate of total amount. Okay, and so then principle 5 is let's just keep going. Make the intervals super small. Make the intervals super small. And we can make them small enough so that we can't distinguish between the exact rate and this pretend rate, and then we'll get something indistinguishable from the exact amount of change. Okay? So this expression then is for when we have not small intervals and we're summing them up kind of like by hand. We think of chunk, 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 and we're adding up all these changes to get the total change. But when things get super small, what is our notation then? That means the exact same thing as this for super small intervals. How do we write this for super small intervals? The same thing, sum up all the changes. That's what integral is. That's what integral is, right? Integral means the same exact thing as sum up all the little changes, but now for super small intervals. So that when we do that, we get a total amount of change that's indistinguishable from the exact total amount of change. It's so close that we just call it even, right? It's so close we just call it even. So what similarities do you see in these notations, right? What similarities do you see? What's that? Change in x, right? So, but now our change in x, so this dx is just like a super small change in x, right? Dx means a really, really small change in x. What else do you see? Rate of change, right? Before we had individual rates of change, but when you make the intervals really small, all those individual rates, what form the? So what is this? That's the rate function, right? So when your intervals are super small, all those individual rates form the rate function. Right? So rate function is all of the rates at infinitesimal intervals, right? As opposed to rates over finite intervals. But it's still m, right? So it's still, these were still rates, and now it's like all the rates, which makes the rate function. What else do you see that's similar?
The Greek S has been replaced by the German S.
That's right. So this is Greek S for sum. Now this is German S for sum. They're both sum. We're still summing up a bunch of changes. It's just now it's a gazillion small changes instead of a finite number of bigger changes. But we're still summing up a bunch of changes. So you see that back to our original thing, constant. Where do you see constant rate of change in this integral expression? Is really important. So when you see this, how do you see constant rate of change? Where do you see it? Where's constant rate of change in there? No? Just f of x? That's the changing rate function, right? What did we say about constant rate of change? Constant rate of change is dy equals? Yeah, William.
I still agree that it's f of x, but it's constant for that really, really small interval.
Right. But remember, our meaning for constant, yeah, absolutely, that's right. Our meaning for constant rate of change was that dy equals? Right, we can get a little bit of change by doing m dx. So I'm kind of saying, where do we see that? That's what I'm asking. Where do we see that in this expression? Is it there? Still there? What's that?
The whole thing equals dy.
When you say the whole thing, you mean the whole thing?
Yeah.
No. It's right here. It's right there. That is our m dx, right? So we're summing up a bunch of little changes in y. We're summing up a bunch of m dx's. So when you see f of x dx, that's essentially dy. And we're summing up a bunch of those, just like you did in the insects problem, and we did in the flag problem. But now we're thinking about super small intervals. So it's summing up, like I said, a gazillion of these, a trillion. Okay, so when you see an integral expression, that function, we're thinking that's a rate function, right? And that whole expression is a little change in y, or a little change in the quantity we're interested in. And we're going to sum up all those little changes. Okay, any questions? Super important. Okay, so we'll go on to principles 6 and 7 here. So back to our flag. Okay, so we're interested in, let's say, now we want to express, first we want to, let's sketch. Can we sketch the height function? So based on this, this rate function that's very close, we'll just call it even here. So it's the interval is so small that it's virtually the same as the original rate function. So can we make a sketch of, over here now, the height function of the flag? Can you sketch just a rough sketch of the height function of the flag? I don't remember what I said it started at, so we'll say it starts at 5. I think it starts at 5. So starting at, if the height starts at 5 meters, the height of the flag is 5 meters at time equals 0 seconds. Sketch the height function. Roughly using the rate of change function. Go. That's your task. Yep, 5. Some of you have nice sketches. Others have the right idea. Okay, so most of you have the right idea, and then some a little more accurate than others, but that's okay. This is a rough sketch. This is what it is. So whenever the rate is negative 0.75, it's coming down at what a constant rate, so it's a constant rate, and then in between hands, it's going to level out for a moment, right? It's going to level out for a moment when the flag's not moving, and then the next pull, and then it cruises down like this. Okay, so now our next task is it's working hard. That's fine. Okay, so the next task is, any questions about that? So now we've got the same time in seconds on the x-axis, and now this graph over here is the height of the flag. Height of the flag, which we're getting from the rate of change of the height of the flag on the left. Okay, so in two different ways, we're going to represent the change in height of the flag. So we'll call this function over here r for rate. Okay, so this is function r. And we'll call this function over here H for height. So in two different ways, we want to represent the change in height of the flag from 0.7 seconds to, so from 0.7 seconds to 1.8 seconds. So over this interval, now, this is no longer estimating, no longer an estimate in the change in height. This is an exact. So from 0.7, I want two expressions that give the exact change in height of the flag over that time interval. Okay, here's a hint. One of those expressions will involve the function r. Other expression will involve the function h. But both of them will represent exactly how much the height of the change of the height of the flag from 0.7 to 1.8. So this interval of time right here, 0.7 to 1.8 seconds. Go, see how you do. So we're going to write one expression over here using function r. And we're going to write one in front function over here using function h, expression over here. Try it by yourself. See, think about it, try it by yourself, and then once you have it, or if you're stuck, then consult others. Good. Yeah, I like that one. This one's not right. This one's not right. I like that one. Is that all you agree? So I don't want just the height function. I want the change in height from 0.7 to 1.8 seconds. Only the change in height. So not the height itself. So I just want to change in height. So you're on the right track. Okay. Okay. So that would be what? This little change for one interval. So how would you do this little change for all the intervals? We want exact. See, that's the right idea. We don't want the exact. So we don't want. There you go. Summing up all the changes we have. See? Okay. So yeah, you guys have kind of made up your own function notation. Remember function notation? I mean, it's your thought, and it's totally right. It's totally right. But you kind of made up your own notation. Do you know how to represent? It's not what I'm looking for. It's just I'm just like what's conventional, right? So what you've done expresses it perfectly. But it's just your own. You kind of made up your own expression of it. Because you don't. So with the input, you usually don't put the input as a subscript, right? So how do you? What's function notation? What standard function notation is? Yeah, you know it. You're not realizing. So like when you have f of x, the name of that function is f. So this is the name of this function is h. That's right. But not, yeah, that's right. Okay, cool. Last we got it. So if we've got the rate function, to get the total amount of change in height, we've got to sum up all the little bits of change of height. Each little bit of change of height is what? Each little bit of change in height is What's each little change in height?
X times d.
Right. Each little change in height is Rx dx. That's right. Constant rate of change. A little change in height is Rx dx. But now that's just one of them, right? What do we want to do? We want to add them all up from 0.7 seconds to 1.8 seconds. And how do we do that? The integral. We're going to sum them all up, starting at 0.7 and ending at 1.8. So an integral expression is the total amount of change at some rate function, starting at 0.7, ending at 1.8, at that rate function. Okay, so that will express the total change in the height of the flag from 0.7 to 1.8. How do we do it using h? How do we express the total change in height of the flag? So this is like pre-calculus. This is easy. We've got the height function, so what's the total change in height of the flag? Philip?
H at 1.8 minus H at 0.7.
Yeah, so we get the height, the final height, minus the initial height. Right? Final height minus initial height. How's that seen on the graph? How would we show that on the graph? This change in height of h of 1.8 minus h of 0.7. Guadalupe, how could this be shown on the graph? What's that? So visually, I'm going to show this amount. This is amount, right? Amount of change. Can I express it visually or mark it off visually using this graph? How could I do that? Okay. How could I represent this amount of change on this graph? Anybody? Okay. We start by plotting the points. All right. So what point am I going to plot? 0.7 and whatever that is, right? So this point represents what? 0.7 seconds and whatever the height is, h of 0.7, we're going to h of 0.7. Whatever that height is. And then? That's a good start. 1.8 and whatever the height is at 1.8. And so then how can I see or show what I've put in the box, that change in height? How's that seen? Ariana? Uh-huh. Right. This is our height in meters. This is our height in meters. So the change in height is this vertical change between these 2 points. And so that's kind of easiest to see what over here on the axis, right? If we take these points like this, then it would be what? This bar right here would represent that amount of change. You see that? Because this y-axis is our height, and so it started here. The height started there, and then at 1.8 seconds it ended there, and so that bar shows us the change in height. Do you see that? It's a visual representation of that change in height. Okay, that doesn't work on the rate graph. Why? Because on our y-axis we have rates, right? We have rates. But here on the height graph, we can use that as a measuring stick of height. So that red bar that I highlighted there would be the change in height from 0.7 seconds to 1.8 seconds. And that change is, what can we say about that change? Just generally? The change is decreasing. The height decreases, therefore the change is negative. So that value would be negative. Okay, any questions on that? All right, so look. These both, what I put in the boxes, both are the same thing, right? Both of these expressions are both the change in height from 0.7 to 1.8 seconds. Therefore, what can we say? They're equal, right? They're equal. So we could say there's 2 different ways to calculate total change, and we can set them equal. We've got the one way is by summing up the lots of little bits of change using the rate. Summing up little bits of change using the rate. The other way is just take the final value of the quantity minus the initial value of the quantity. So this is principle 6, I think. Principle, or 7? Where are we at? 6? Principle 6. Principle 6, there's two ways to represent the total change of a quantity. Using an integral expression and the rate, summing up all the little bits of change, and then using the quantity function itself. Just take final minus initial. Last principle is now, how does the function h relate to the function r? How are h and r related? Okay, so which is the derivative of which?
H would be R is the derivative of H.
She's saying that r is the derivative of h. People are nodding their head. Is that right? Right. No?
Yes.
Yes. R is the derivative of h. Why? Because if h is our quantity function, r is its rate of change, right? H is the height function, r is the rate of change. So r is the derivative of h. So then, therefore, what is h?
The antiderivative of R.
H is an antiderivative of r, right? H is an antiderivative of r. Okay? In fact, there are many, and it could be any one of them. Okay? No, actually, so if it's our true height function, there's only one. Okay? But yes, h is the antiderivative of r. Principle 7, and we're done. We've got it. That's the fundamental theorem of calculus, that there's two ways to find the total change. By the sum of little bits of change, like your homework, but now just an infinite number of them. Or you take the final value of the quantity minus the initial value of the quantity if you have the quantity function. And that quantity function is the antiderivative of the rate function. That's it. We got it. Does it make sense? So, two ways to represent an amount of change. Using the rate function, you might have already written this down, or using a quantity function, final minus initial. And then principle 7, the quantity function, capital F, is the antiderivative of the rate function, little f. That's what the fundamental theorem is about. Oops. Sorry. Anybody have a question? So let's practice here. Oh, so some notation. So when we write that total change as the difference in the quantity function, final minus initial, this side, you'll see this notation also. They'll just write the function once, and then with a bar after it, they'll write the lower limit and the upper limit. And what that means in red there is exactly what's above in the red box. Those are exactly equivalent. This thing right here means take final value of the quantity at B minus initial value of the quantity at A. So it means the change in the quantity starting at A and ending at B. So you'll see that in textbooks, and we'll use that as kind of a compact notation to mean the same thing. Okay, so let's practice. For each one of these expressions, we want to practice verbalizing this. Practice verbalizing the meaning of the whole expression as based on the parts that you're seeing, right? So we're explaining the meaning of expression, including all specifics. Practice saying back and forth to each other what it means. Then we're going to write a computable expression that gives its value exactly. So the thing about an integral expression is it's reflecting this very complicated process, but it doesn't give us a value, right? We know it's a total amount of change, but it's more a reflection of the process to get that total amount of change rather than an easy way to compute it. The other side is the easy way to compute it, right? So that equivalence statement where you have the quantity function, you do finest minus initial, the advantage to that is it's generating that value. So we're going to write a computable expression that gives value exactly, and then solve or simplify if appropriate. Okay, so there's going to be lots of talking here because you're practicing expressing the meanings of these expressions. Let's do the first one together. Anyone want to try the first one? That's right. Tell me your name again.
Alvaro?
Alvaro? What is the meaning of the integral from 1 to 2 x to the 4th dx?
I think it means that we're going to evaluate the expression from everything from 1 to 2 with the expression x to the 4th dx.
Okay, but what is it going to give us? So that when we evaluate that and get a number, what will that number be? Jacob, want to try?
It's going to be change from 1 to 2.
Okay. Which change from 1 to 2?
I mean, it's going to be the change in the accumulation function.
Okay.
Using the rate of change function x to the 4th.
Right, right. So it's the total change of some accumulation or some quantity from 1 to 2 when? The rate of change is x to the 4th. You see that? It's going to be the total change in the quantity as x goes from 1 to 2 when you're going at a rate of x to the 4th. Okay, so, and then you're going to write out the computable expression and solve it. And remember, so the quantity function is how related to the rate function again? So this quantity function that we're going to use to compute it is how related to the rate function? It's which one? So this quantity function, is it the derivative or the antiderivative? Antiderivative, right? Because the rate function would be the derivative of the quantity function. So to get the quantity function, we're going to do antiderivative of the rate function. Okay, go. Go. Talk them out. Talk them out. Practice. So for time's sake, let's just do A and B for each. Let's not do the crunching. Do A and B for each. I'm going to make sure we get A and B for each one.
So second dash the total change function from 0 to 8 when the rate is 3 to the x. I've never set these. Yeah. I guess. Yeah, it's just equal to 3x. Yeah. Yeah. That's just equal to 3x. it's just the total rate of the total change. The quantity from negative 3/4 from the changes.
No, it's either the x, it's either the x plus the derivative of the inside, which is 1. Either the x from 0 to 8, which would be 1,
It's just the total change in quantity from 10 to 35 when the rate of change is 2x times the square root of x. I guess we're forced to substitute that. The next one down.
See if you can just write the antiderivative without. Did you say substitution?
Yeah.
See if you can just write the antiderivative down. This one's kind of easy, just without doing all that, because that's the way we're going to learn it. We're going to try to learn it, just do it by looking at it. You can do this so much faster. So what we want to think about is like, okay, you just did the chain rule and you got that. So what was the function that gave you that as its derivative? Nice. You can do it. You can do it.
So that's right. So the derivative of cosine is negative sine. So therefore sine will be negative. Remember that. Yeah, I've already done that. Yeah.
Okay, so I kind of actually maybe most interested in part A. So I want to hear someone this second expression. Can you explain the meaning of that second expression? Tell me your name again. Allison. So what's the meaning of that second expression, that second integral down?
So the total change in some quantity
Uh-huh.
from 0 to 8 when the rate of change is equal to 3 to the x.
You hear what she said? She nailed it. It's perfect. Okay. How about the next one? Let's see who's Adrian.
Oh,
The third one down. What's the meaning of that third expression down?
that's all the small changes from negative 1/2 to positive 3/4, or summing of all small changes from negative 1/2 to 3/4 when the rate of change is sine x.
Good. And when you sum all the small changes, you get
The
total amount of change, right? So yeah, it's the sum of all the small changes from negative 1/2 to 3/4 when the rate of change is sine x, and that gives us the total change. Okay, and then I wrote the answers to B for those. What about this last one? So if we're doing antiderivative, do we recognize this as the derivative of something? What kind of derivative is that? It's a little more complicated derivative. Do you recognize that as the derivative of
x squared
Do you see this 2x is the derivative of the inside? What rule is that? So this, do you see that this is kind of the result of a chain rule derivative there? So what function, if you took the chain rule on it, would you get that? What function, if you did the chain rule, would you get that? Yeah, so it's really you just, basically you took the derivative of x squared plus 3, what, to the 3 halves. But if you have 3 halves, you need 2/3. And so if you're not sure, so it's like, what can we do if we're not sure? Take the derivative of your guess, right? Take the derivative of your guess, and it should be exactly that. And if it's exactly that, then you got it, right? So, and that's the way we're going to approach these. We're going to be on the lookout for rate functions that are really just chain rule. And then we think, okay, what function, if we did the chain rule, would give us? Would give us that derivative. Well, we know that in the chain rule that 2x pops out, so we're not going to have that 2x, right? It's going to come from that x squared plus 3. So it's really just the power rule on that square root, right? So it's going to be 2/3 x squared plus 3 to 3 halves from 10 to 35. So that's what we're going to do next. So the next part of the course is, now that we know we have a good firm meaning for integral and the fundamental theorem to get solvable expressions from the integrals, we're going to be, the next part of the course, about a week or so, is integration techniques. So when you have weird and hard and complicated rate functions, how do you get the antiderivative?